Simon.
Sorry?
I just started it.
Oh, okay, perfect.
Okay, fantastic. Well, welcome everyone, and thanks for joining us for this safety review. And I think how we'll do this is I'm imagining you have some kind of presentation, and I think I heard you talking to Bram before I got on here. We'll do our best to just let you do your presentation, and we'll ask questions at the end unless we have some burning question as we're going through this. So I'll shut up now and let you present.
All of our slides should be numbered, so if you have, you should be able to reference slides pretty easily.
All right, everyone can see the slides, just confirming?
Yes.
Sweet. So, yeah, we can get started. So we are InSpace. We are Carleton University's rocket engineering design team. And this is our critical design review for the Spaceport America Cup this year. So just an introduction, which will be done by myself and Simon Galla. So yeah, just a very quick intro, just so you guys have a background of our current experience. We were founded in 2014. We're the rocketry team at Carleton University. We have launched successfully at the Spaceport America Cup 4 times, and we are currently the largest design team at our university. In 2017, we launched the rocket called See You Later. There was a successful launch. The rocket went up. We did not recover it. In 2018, we had a successful launch and a successful recovery. However, this rocket had a main at apogee. In 2019, we launched Chef Boy Apogee, which again had a successful launch and a successful recovery. Our GPS worked this time. We found our rocket pretty flawlessly. In 2021, it was virtual, and so we did not actually construct an airframe that year. And then in 2022, we launched successfully last year with McNominal, and the recovery was a little bit faster than we'd like, so we encountered some damage on recovery.
So yeah, to go through a little bit of what we're doing this year. Of course, we're building a 30,000 foot category COTS launcher. This is the first time that we've launched to 30,000 feet, so we have had to redesign our previous airframes to optimize for the low weight and higher thrust. That means that we've shifted to a primarily composite airframe as opposed to the sort of more metallic airframes that we've used in the past. And for the first time for us, we are developing a fully integrated fin can. We'll go through that in a little bit more detail in the aerostructure section. We're also developing a 3U CubeSat standard payload with the pointing capability. Again, we'll go into some of the challenges that we've had with that in a bit. And finally, on the sort of software and avionics side of things, we have a payload uplink and a ground station that we are developing to get some telemetry from our rocket. So to look a little bit at what our team would define as a success this year, in terms of our launcher, we're aiming for approximately 30,000 foot above ground level apogee. As Brendan mentioned, we have never had a fully successful recovery, so we're looking for drogue deployment at apogee, main deployment at 1,500 feet. All of the components of the launch vehicle should be tracked and recovered in such a state in which they can be disassembled, inspected, and relaunched so as to maximize our points at the Spaceport America Cup. On the team side of things, we are also in parallel developing a hybrid engine. This is not something that is flying at the Spaceport America Cup this year, but something that we have been working on for a number of years and hope to fly in the near future. The target for this year is a cold flow of our hybrid engine. As far as the design is concerned, we're looking to transition from the 10,000 foot to 30,000 foot competition category. And in terms of our outreach, Brendan mentioned that we're the largest design team on campus. As that is the case, we have the opportunity to do a lot of outreach and sort of be a real force for good in the Carleton community. So we're trying to continue our social media outreach and really grow the team in that way. And then this year we have a number of graduating team members who have sort of played an integral role in getting the team where it is today. We want to make sure that we carry over the growth, structure, and success of the team to a new generation of executives and members. And this is our team structure. So you can see all of our executives. We have about 21 of them. And then the team members, about 120 or so people in total. So we have a pretty big team to deal with.
How many are you bringing to Spaceport? I'm sorry to interrupt there.
There will be 23 of us coming
Okay.
to Spaceport, so a good contingent. Yeah, and without further ado, I'll pass it off to our aerostructures lead, Kieran.
Hi everyone, I'm Kieran, yeah, I'm the lead aerostructures team member for InSpace this year. So I'm just going to be here. This camera's way too low for me. There we go. That's better. Okay. Yeah. So I'll just be going over the overall structure of the rocket and how everything's going to work and how we're going to get to 30,000 feet or close to it at least. Where's my mouse?
Use the arrows.
Oh, okay. Yeah. Sure. Yeah, so this is more or less what the rocket's going to look like. So on the top, you have a render here, and we're going to paint it bright yellow and make it all kinds of fancy. And then down here, you have more of a kind of, I guess, graphical representation of where everything sits in the rocket. So at the very back here, you have the aft frame, and that contains the fins, the motor, and the drogue chute. And then in the middle here, you have the avionics tube, also known as the center tube, that has all the avionics stuff in it, and that's pretty much all it has, which is still very important, but that's what it has. And then the forward tube has the main parachute, and then above that you have the payload and the nose cone and everything else that's in there. Yeah. So first I'll start at the aft frame, and then we'll move forward. So the aft frame is basically constructed of two concentric tubes. I wish I had this in person to show you guys, but it's actually downstairs in the composites lab right now. So I personally can't show you that, but I can show you these nice pictures. So essentially what it is it's a central cardboard tube, which is not load bearing. It's entirely just there to keep the motor centered and in place during launch and stable. And then outside that, we have an outer carbon shell, and that's the structural component where all the load is transferred through. So the way that it's kind of assembled is you have the cardboard tube, then we glue the fins on the cardboard tube, or we use really thick epoxy, which worked well. We use our fancy alignment jig here just to make sure everything is nice and straight. And then what we're going to do after that is we're going to build up this outer layer here outside of it. So we have, show you, basically these little foam inserts. And so where this will sit is between the inner cardboard and the outer layup. So it'll sit like this for the boat tail. So you see how it tapers down. And then the fins will go in this kind of cutout section here. So together, they kind of all form one piece. And then we'll just do a tip-to-tip layup over all of this. And then we'll get our outer shell. Now, that's just the boat tail section. For the kind of linear section, I guess you could call it, we have an off-the-shelf carbon tube. So we're just going to mount that to the tapered section using a small kind of, tube-in-tube coupler, all made out of fiberglass. And then we're going to use wooden centering rings just to keep the motor tube concentric, because again, it doesn't need to transfer any load. It just has to be as light as possible and keep everything central. And other than that, we have our aluminum thrust ring right here, which is held in place by this clamping mechanism here. And then we have our retaining ring, which is basically just to stop the engine from falling out of the rocket if there's no thrust on it. And then the motor slides into there, gets clamped down there. The thrust is transferred from the motor into the thrust ring, and you can see there's a little gap there, and that's actually done on purpose because this tube in the middle is supposed to be cardboard colored. But basically, when we want it only to transfer load to the outside. So we want to be able to control where the load is going. We don't want it to unpredictably go through the center and then just tear out and shoot through the center of the rocket, because that would be bad, to say the least. So yeah, that's why we have that little gap there, basically just to control our load path so it goes through the outside. And then of course at the top we have our fiberglass coupling tube, and our eye bolt is mounted directly to the motor. And then lastly, we have a very simple bulkhead here just to aid in the recovery procedure of separating the rocket in half there. And then Brendan, do you want to go over our motor selection?
Yeah. Okay, so just on the motor selection, so we are going with a Cesaroni 03400 reload. So we were, I believe, one of the two teams at least from Animal Motors, that managed to secure a 03400 reload. We ordered like a very long time ago, so it worked out pretty nicely. Why are we choosing an 03400 reload? Well, those are the top three, I believe, in Impulse 6-grain XL casings or motor reloads for Cesaroni casings, and it clearly has the highest or like closest altitude to 30,000 feet. So in order to not increase our motor casing diameter to a Pro 150 case, which is one, hard to get, and two, pretty difficult for us to integrate, we chose to just go with the 03400 and stick with a 98 millimeter motor casing. So you can see all of the specs there, but yeah, pretty much we're getting up to about 27,000 feet, which we believe is acceptable for our first time flying up to 30,000. Yeah, we'd like to get a little bit higher, but we think that this is acceptable for this year.
Yeah, it's the first attempt, so.
So back to Kieran.
Okay, thank you, Brendan. So next I'll be going over the tubes kind of in order from the aft frame all the way to the front. So like I mentioned, that's what the inner tube looks like. It's just simple kind of coated cardboard, not load bearing, just needs to be as light as possible and precisely fit. And it's actually specifically for this purpose, so we have confirmed it fits the motor casing very nicely. So body tubes. We've had some issues in getting the body tubes, where we ordered them from a very nice company in Utah, because that's the best supplier that we could find. And they basically split up the 3-part shipment, them being UPS, and delivered it to someone named Sergio. We don't know who Sergio is. We never found out who Sergio is. So somewhere there's a guy named Sergio who has a approximately 9-foot long carbon tube. I don't know what he's doing with it, but I hope he's finding good use for it. But the company was able to get us a new one, so that all got sorted out. So this is what the middle body tube or avionics body tube looks like. That is the only body tube that is fiberglass, and the reason why it's fiberglass is for radio transparency, so that avionics can actually see through it. Well, see through it metaphorically, you know what I mean. But yeah, that's the avionics body tube. So that's that little short section in the middle that I showed you earlier. Then we have the upper body tube, which is the very nice, fancy, kind of wound carbon fiber tube. And the aft frame linear section is made from the same tube. So both of those are carbon, and then there's kind of a fiberglass sandwich in the middle. And then you have the couplers, which are exactly the same as the avionics body tube, except they're a little bit smaller, so they fit within it. So basically you just have one coupler, or you have a tube, the coupler goes halfway into one tube, halfway into the other, and then it joins them together. Except actually, I'll explain here. So with this coupler here, basically for the very lower and upper couplers, half of them is rigid, like half of it is rigidly mounted. The other half of it is temporarily mounted with shear pins. And the reason why is because for recovery, it has to split here and here. So that's just an important detail that I'd mentioned. Yeah, so of course, for the recovery system to work, we need bulkheads. So the bulkheads serve two purposes. They are A, pressure sealing, and B, they provide hardware for recovery. So that involves the CO2 ejection system, which pressurizes the rocket, causing it to split in half, and also an eye-bolt hole in the middle so that we can actually mount the parachutes to something. We have an A and a B configuration. So this is the A configuration on the left, and that's the B configuration on the right. Both of them serve the same purpose. It's just one of them is mounted in tension, whereas the other one is mounted in compression. And the reason being is because it makes assembling the rocket a lot easier. So either we put it on top of the shelf or we put it on the other side of the shelf, and it either pulls down or pushes up, kind of idea. And then, yeah, here's the mounting shelf. So it's just all this made out of aluminum, but it just kind of screws into the body tube, and then we epoxy it in, and it'll create a nice seal when we put a gasket between the bulkhead and that. And then we also did some FEA on it, and yeah, we're well below the yield strength, so notes in there. Okay, now the nose cone, I actually have some more parts for the nose cone. So we actually do have part of the nose cone laid out, but we can't show you that again because it's locked in the composite lab. But yeah, it's pretty simple. We tried to keep stuff simple for this year, as simple as possible, to make everything as light as possible. But essentially we have student research and design carbon fiber nose cone. I'll go over how that's made in the next couple slides. An aluminum tip, and then the payload mounted in here. And the way that that works is we have these little blocks here, which is basically you're adapting a circular hole to a square hole, and then it bolts to the payload. So these here are both screwed in and epoxied, and we have one of them that has a hole for the eye bolt for recovery. And so that's how we're doing the eye bolt up there. And then here's our nose cone tip. It's very shiny. So, and then there's a little eye bolt hole in the top there. So yeah, I'll kind of go over really quickly how we're doing the layup for the nose cone. So the idea in the past, we've done just wet layups where we kind of do it in 2 or 3 parts, and we just lay the sheet stock over, and then we paint on the epoxy and do that kind of stuff. But this year we're trying something a little bit different where we're using sleeve stock carbon instead. And it's supposed to simplify stuff a lot, and so far I think it has. It's simplified stuff a lot. It's given us a better overall result, so we're really happy with it. But essentially you have positive mold, which is the size of the nose cone minus the thickness. You overlay the sleeve stock over that, and then you have a negative mold that kind of goes around all of that, and then you vacuum bag it, and then you have a nose cone. And the reason why we have the negative mold is just for surface finish. So it's just to make sure the outside is nice and smooth. So yeah, there's some pictures of us assembling it. So you can see there's the 3D printed positive mold with the sleeve kind of just placed over it. And then that's it with epoxy all over it. So that's what we were doing the other day. Yeah, and then here's the diagram of how the payload mount works. So you have the bolt going through, it's epoxied in, and then you're basically just creating a circular hole and converting it to a square hole so that we can mount the payload in. And then lastly, this is how the avionics mounting works. So essentially you have the 2 bulkheads that I was talking about before, so the A and the B configuration, and the avionics system sits nicely between them. So it's really simple. It's just mounted on a couple of threaded rods and with some coupling nuts. And so that's how it works. I mean, this is sideways, obviously, but it basically hangs underneath the upper bulkhead and sits right above the lower bulkhead. Cool. Okay. I will now be passing it on to Mateo. Thank you.
Hello, my name is Mateo, and I am one of the upcoming junior leads for the next year, and I'm filling in for our senior lead who could not be here today. If I could get the next slide, that would be great. Thanks. So our design for the avionics system this year involves the implementation of a modular SRAD electronic system, as well as several COTS components implemented separately from the SRAD system in a dual redundant configuration. The SRAD system includes a GPS board that is transmitting to a ground station receiver on the 433 megahertz low rad band. Several of our members at competition are licensed to use it, and our COTS system uses 2 Easy Mini systems in a dual redundant configuration, so they have separate power sources. And we also have a featherweight GPS unit for recovering the rocket, which has its own power supply and arming switch. So we have the 2 Altus Metrum Easy Minis on the dual deploy system, the featherweight on 900 megahertz, and a 2-stage arming system for deployment. So our first switch engages the SRAD power and the first Easy Mini. The second switch connects the E-matches, and the third switch engages the second Easy Mini. And I'll hand it off to Aaron from Payload and Zach.
Hi, I'm Aaron. I'm the payload lead for this year. Zach unfortunately couldn't be here today. So to start off, our payload, we're going with the 3U CubeSat standard. This is continuing over what we've been developing for the last 3 or so years. What's different this year is it is staying static, stored within the rocket nose cone, as you saw earlier. We have to not deploy as originally we had planned to deploy due to some complications with the aerostructures. So we had to kind of change our scope in the last couple months. So instead, we're going to be collecting and evaluating a lot of engineering data to be collected during the flight. We're also going to be testing our SRAD components within the launch environment. Now, while we can't fully functionality test them, we're going to be testing them structurally to ensure that they're functional during and post-flight. And then all of this data is going to be stored locally and then processed post-flight due to being unable to transmit data from that part of the rocket. So we have a number of COTS electronics on boards that are going to be supporting this data collection. And we have designed to integrate with our SRAD stacks, basically perf boards to go into the stack. I actually have it on the next thing there, where we have a stack where we can stack together our COTS and SRAD components. We're going to be using a number of Arduino-based microcontrollers, very small ones they're about square centimeter, 2 square centimeters footprint. So we have quite a few of them on board. We're going to be collecting vibrational data using a 6-axis inertial measurement unit. We're also going to be collecting trajectory data from GPS and altimeter. Of course, making sure that these all work while within the rocket gives us more confidence for future launches wherein we may be deploying from the rocket. Additionally, we're going to be employing strain sensors to observe tensile loading, specifically on the recovery eye bolt attached to the payload, because we'd like to get data on how much force is actually provided during launch recovery, which will be useful in future years. Obviously, we're not recovering this year, or we're not deploying this year, so that's not going to be useful data, but we'd still like to test these, test it in the launch environment to make sure that it can still work. The stack is basically the stack as you see here. They're using 304 stainless steel standoffs for compatibility with the rest of our frame. Additionally, we have 40-pin buses, which will basically transfer signals of 3 and 5 volts. The COTS boards, we're also going to be employing their own SD cards in order to save data locally and process post-recovery. And like I said, we have SRAD boards as well, but they're going to be mostly inactive and just tested afterwards. Okay, these are kind of the components we're going to be testing that we developed. So, the structures are SRAD and new for this year. We also developed a solar array, strain sensors, as I mentioned, a power management board, a command and control board, a navigation board, and finally a reaction wheel, which was developed a couple years ago. Okay, moving on to the frame itself, constructed of 304 stainless steel, and basically is designed for the bottom to drop out so that we can very quickly swap electronics in the stack. It's been the side panel has been laser cut and bent, and is being assembled with bolts and rivets because due to the nature of 304 stainless, we can't weld it. And yeah, this is just an iteration over again the past 4 years, keeps that standard. The internal frame is going to have mounted to it 4 solar panels. Each solar panel will have 16 cells. It's going to generate about a peak of about 37 volts. And it's going to be sandwiched with a polycarbonate panel on the outer face and solar cells and epoxy resin with a kind of spacer that's been 3D printed using chopped fiber filament bolted to the frame. And so obviously it's inside of the rocket. So it's not going to be generating any electricity, but we would still like to at least verify its functionality within that environment. Finally, just additional information about our payload. We'll be arming it with a key switch during rocket assembly. No remote arming. To account for this, we've sized the battery to operate for 24 hours, which should give us enough time for proper recovery. And then finally, we're going to be having a camera on board facing downwards to hopefully obtain footage of separation when the nose cone separates. So thanks. I'd like to pass it on to recovery.
Hello, everyone. It's nice to see you all. I'm Paige. I'm recovery's lead for this year. So I'm going to talk about 2 parts of the recovery system today. First, I'm going to talk about the deployment method, and then I'll talk about how we are making our parachutes. So for the launch configuration, we have the payload that is stuck inside the nose cone, as you see at the top, and there's 2 detachable bulkheads that Kieran discussed earlier. At each of these bulkheads, they're the Raptor CO2 ejection systems, and essentially they are used for a dual brake deployment. The main parachute is in the upper compartment of the body tubes, and it is bagged as of now, and is connected to the nose cone and the avionic bulkheads. While the drogue parachute is not planned to be bagged, and it's in the lower compartment, connected to the lower avionics bulkhead and the motor bulkhead. All shock cords will be connected to the bulkheads via eye bolts, as Kieran discussed earlier. So at Apogee, the drogue will be deployed by deploying the CO2 ejection systems just below the avionics bay. This will allow the carb compartment to open and the drogue parachute would be deployed. We're actually using 2 Raptor systems just with different threading. We're not using Peregrine system. Sorry. They're both from Tinder. Sorry, the Raptor system is from Tinder Rocketry, and they worked with our recovery system last year. The bulkhead will separate from the lower body tube and the drogue parachute will deploy. Under drogue, we want the parachute to fall down at target speed of 115 feet per second. However, the drogue that we made as of right now, unfortunately has an expected descent rate at below 90 feet per second, very close to the limit of 75 feet per second. And so we're actually going to make another parachute soon to fall at a faster speed. But as of now, we do have 1 drogue made. I will discuss it a bit more later. It will be connected at 2/3 of the shock cord closer to the avionics bay, such that it is 10 feet from the avionics bay and 20 feet from the motor bay. And it'll be connected to the shock cord via a knot and a knot that is attached to a slip ring that is attached to the shroud. At 1,500 feet, the main parachute will deploy by the upper CO2 ejection systems deploying. This will allow the upper body tube and the nose cone to separate. Here is where we're having a bit of issues and we would appreciate some feedback. We want to have a main bag for our main parachute such that the shroud lines are fully in tension before the actual canopy gets under any tension. This is so that the risk of any shredding happening is minimized. So we have 2 options that we are considering for the deployment of the parachute out of the main bag. The first one is shown here on this slide, where we have the line passing through the main bag, outside of the main bag, but connected to it via elastics so that it just passes through. We would want this line to be longer than the shroud lines, such that as the nose cone is being pushed away from the body tube, the shroud lines are going to be under tension before that longer cord is. And this hopefully would be enough to pull the main parachute out of the main bag. I am concerned that this will introduce tangling, potential for tangling, or all the force will just go through this longer line and nothing will go through the suspension lines and the main parachute will not deploy. Our second idea is to have a pilot chute at the top of the main bag. Essentially, once the body tubes separate, the body tube and the nose cone separates, the pilot chute will pull the main bag out, and with the shock cord at the bottom pulling down on the main parachute, it will pull the main parachute out of the bag. We only really started considering this a few weeks ago, and we would appreciate any feedback on this. The pilot tube and the pilot chute and the main bag will be attached to the main parachute at the top by a string. And that's pretty much what we have for this so far. The pilot chute is in the process of being made as well. So we are gonna have these options available until last minute changes if needed. Another option is just not to have a main bag, but I would prefer to have a bag. Up for discussion. Under main descent, we want the main parachute to fall at 15 feet per second. This is how we have sized the parachute. So as you can see here in the photos, the parachute has been made. It is unfortunately too big for us to put in our wind tunnels or do our truck testing, which I will discuss later. So we don't really know for sure if it will fall at this speed, but it is gigantic and very strong. And I am very confident that it will be well below 30 feet per second. Like the drogue parachute, it will be connected on the shock cord at about 2/3 of the length from the avionics bay. So 20 feet from the avionics bay and 10 feet from the nose cone. This length will have to be lengthened if we do the method with the line passing through the main bag instead of the pilot chute, to be discussed later. So as for making the parachutes, we are using ripstop nylon. Our drogue parachute is currently red and our main parachute is green. We have it all all the gores are sewn together with a French felting, so it's kind of like this, and sewn together with high strength thread. And over top of that, we have the nylon seam tape. We just call it ribbon. And the parachute has a shape of a biconical parachute, or at least we tried to, given the handbook we were using, the instructions from that. And with that, we brought the parachutes into wind tunnel testing. This is the facility we have here at Carleton. It is unfortunately not amazing. It has a lot of turbulence, and we essentially have attached the parachute to a load cell on the bar behind the parachute here. And in order for us to get accurate readings, it needs to be perfectly aligned with the load cell, but without restraint. I'm gonna mute this because it's very loud. The drogue parachute here likes to just kind of bounce around. I don't know why it's not playing, but trust me, it is very chaotic. So in order for us to get a decent reading, we have to kind of restrain it here. The main difference is the first video, it is chaotic. The second video, it is relatively stable, except that we are restraining it, and that does change the geometry. So our results from this are not ideal. However, the coefficient of drag values we are getting are way exceed what we want to get and make us worry that our drogue will cause the rocket to fall way too slow. So this is why we're going to be making a smaller one, and we will put it through wind tunnel testing as well. Because the wind tunnel testing is not incredibly reliable because it is so turbulent in there and we don't know if it's actually accurate. Also, wind tunnels, for it to be completely accurate, you need them to be much larger than the parachute. We decided to visit Area XO, which is a autonomous vehicle testing location here in Ottawa, where they pretty much have long stretches of roads that they let us go visit. Sorry, I'm having trouble. And we attached a 13-foot bar to the back of a truck, such that the parachute could be attached at the very end and have the truck travel down the road at around 80 kilometers an hour with a load cell at the end of the bar and try and see what kind of readings we will get from that. It was also very chaotic. Every single time we went there, there was a lot of crosswind, so it was hard to tell if the blowing around of the parachute was actually from the aerodynamics of the truck or a crosswind, but the results we were getting from this were similar to that of the wind tunnel testing. Basically saying that our drogue might be too big for us. So we are going to be remaking that. And I believe that is it for recovery. I'm going to pass it off back to Brendan.
So yeah, just final words before the question period. There are a lot of people that help us out through our development and give us money, and we would like to recognize them. So they're all up here on the slides. We'd just like to do a quick thank you. And with that, we can bring in the question period.
All right. Thank you very much for that presentation. I think I saw Jimmy Yan join us a little bit late. So I've just whoever is running this, if you saw him come on, I hope you allowed him on board. But I don't see him.
He's in here.
Yeah. Okay. Terrific. Today is the 21st of May. So that means exactly 1 month from today, we are flying rockets at Spaceport. And I'm a little concerned because you have no rocket to show me. So can you give me the status of, I mean, how far away are you from integration of the rocket?
So we expect the body tubes to arrive on the 29th of May. This is unfortunately the reality that we find ourselves in. The majority of the components, with the exception of the final aft frame layup, are otherwise complete, which means that we can get onto integration the week of the first week of June,
Okay.
and allowing us to do ejection testing the week before we leave for Spaceport. It's going to be tight, but that is the hand that we have been dealt because the body tube situation was not under our control.
Yes, right, because they went to some strange person that you didn't know, or they're delivered to them. Yeah. Okay. All right. So it's a. I don't know if you've been at the Ezra Facebook page where they were showing some of these presentations. I mean, a lot of it was laying eyes on the rocket for the first time, and obviously you're still waiting for a pretty key component to show up. So we can't do that part of it. I was going to point out, I was looking in some of your slides, I see you wearing respirators, and the respirators have the magenta on the top of them, and that's for particulate. But then I see them with a white band around them, and that's for acid gas. And I'm just wondering if you've selected the correct cartridge for your respirators.
If I'm not mistaken, the cartridges, or at least when I purchased them, the cartridges were listed as good for organic vapors.
I saw some. I mean, in one of the last slides, I saw some that were the magenta with the yellow band. The yellow band is organic vapor and acid gas. Yeah. Okay. Right here. Stop here. You see the gentleman on the right. I see a yellow band with magenta. That is the combo. It's organic vapor, acid gas, and then the magenta is for particulate. The person on the left, I see a white band around it. That's an acid gas cartridge, and wholly useless for what he's working on. So check all of your cartridges and make sure that they're proper for. It looks like the young lady behind the guy with the has the white band on them too. So
we will double check our respirators in that case.
Yeah. Just make sure because the primary hazard, I think, that you're trying to protect yourself from in that case is organic vapor.
Yeah.
So yeah. Okay. So anyhow, that was just a footnote. Boy, a little difficult to challenge your rocket since it's not here. Jimmy, if you're on here, what have you done with teams that find themselves in the same situation?
Well, this is the first team I've encountered with this particular situation.
Okay. All right.
Can you hear me?
Yeah. Yes. Yeah. Absolutely.
What I would ask is what has been completed. Apparently, your parachutes are completed and they look pretty good. And I'm sorry I'm checking in late, but have you built your payload, your avionics bay, your avionics? What has been done so far?
So the avionics bay is complete. The payload bay has to be finally assembled, but the parts are complete. The majority of the components that we have access to, so that is to say the nose cone and the fins that sort of we have produced ourselves, have been constructed. The bulkheads and internal components have been manufactured. We're really just waiting on the body tubes to complete the final sort of assembly.
Well, out of curiosity, what is the deal on the body tube? Has it been ordered from someone?
So I can kind of go over what happened with this. So basically, we ordered the body tubes from Utah pretty early on in the season, and so that's why we have pictures of them, because at one point they were here.
Right.
And it was basically a carbon fiber stock tube, and then one fiberglass tube for the couplers, which is smaller diameter, and one fiberglass tube for avionics bay. And the intention was that we cut them and then do everything ourselves. Then it would have been early winter semester. We got some additional funding from the school. And so we decided that instead of us trying to sand down the coupler tube and get everything fitting properly, we actually reached out to the company and they said, oh, well, we have this like really slick sanding jig, so we can just do it for you for X amount. So what we did is we basically shipped the tubes back to Salt Lake City to have the work done, and then they shipped them back here. But what happened is on the way to Salt Lake City, despite going through, like, I have an email chain with them about 30 emails long. I probably called them about 50 times. I spoke directly to UPS. I actually went and hand delivered them to UPS. They somehow managed to split up the 3-part shipment and deliver the largest body tube to some guy named Sergio. So what is then faced with is another 30 or so emails and dealing with UPS both saying that we had a claim submitted, that we didn't have a claim submitted, that the package existed, and that the package never existed. And so eventually all of it got sorted out, and the body tube shipped last Friday, or I guess, yeah, like this past Friday. But of course, dealing with all of that took a lot of time. Like if we hadn't had to deal with that, we would be at least like 2 weeks or 3 weeks ahead, because that whole debacle took a good 2 or 3 weeks. So it's unfortunate. I handled it as best as I could. I was calling UPS almost daily at a certain point, but yeah, it's just the way it is. So it is actually, I believe they're shipping it all as one package this time as well, so that there's less risk of everything getting split up. But yeah, I've been tracking it diligently. It's on the way. It'll be here soon. So
Could you someone from the team just keep me updated on the status of the material and your rocket? What we're really trying to avoid is teams in the parking lot at the convention center gluing fins on a rocket. Okay.
Oh yeah, well, we have like that part is custom. So that part we're doing ourselves. Like I showed the picture.
Right. No, I was just speaking somewhat tongue in cheek. Just I'm saying that we need you to bring a rocket that is largely ready to fly.
Oh yeah, no, absolutely.
Short of the inspection that will be done on the Tuesday before the launches. Yeah. But okay, yeah, keep me updated on the status of your materials, and then maybe. Okay, and then Simon, maybe perhaps once I don't need to see your rocket when it's pretty, with the yellow on it and all that kind of stuff. But when you have a fully integrated rocket, if you could send me a photograph of that,
absolutely.
So I have some evidence that things are going well on that. Let's talk about propulsion a little bit. You mentioned that you were one of the lucky few teams to get your hot little hands on an 3400 reload, which is good. I trust you also secured a 98 XL casing for that. Okay.
Yeah.
All right.
It is in the other room.
Okay. All right. Just so it's not it's the XL. It's the longer.
It is the long boy.
Right.
We flew a regular 6 grain last year. So.
Okay. And then you saw the new one and you said, "Holy Hannah, this is a big motor." Yeah. Okay. You're aware that the 3400 you have to bond. You like physically glue those into the phenolic. So, and that's probably something that's going to happen in the United States. I can't imagine that you'd be able to do that in Canada and work away. Okay. So that adds just another layer of logistics for you, because you're going to have to bond those, and it has to sit for 24 hours before you load that into your casing. So just start thinking about, where and how you're gonna do that, and don't say hotel room. Okay.
Yeah. So we've already actually contacted our motor supplier, which is Animal Motors, and they're already there, or they will be scheduling people that can come before, like, to them. So I don't know what their location on site is, but basically assembling the motors and gluing everything with supervision.
Okay.
So we're planning on doing that the day, after the convention center or something like that, whenever Animal Motors is setting it up. So we've already called them. They've confirmed that they're doing that. We just need to call them closer to the event to actually schedule us a time slot.
Okay. Yeah. Well, yeah. See, the big part of it is that you're going to have to let it sit afterwards and allow that to cure. And
we're hoping to do it before the first launch day. So.
Okay. That particular motor is somewhat notorious. But I think a lot of it is legend and lore. Okay. I mean, I personally have done 11 3400s, and all of them were successful. So just read the directions, and you have to be very intentional. If you take too much time between those grains, the curing agent starts doing its thing, and it can get really hard to shove those grains into the phenolic. So a kind of a stressful scenario. But if you're going to have somebody who's already done this with you, from Animal Motor Works, I think you'll be in good shape.
Yeah.
So, okay. That's all I had on the motor, and you're using the CO2 for your ejection. So, and I also heard 30 feet was the length of your cords, right? For the shot cords, harness, whatever you want to call it. Yeah. Okay. All right. Jimmy, do you have any? I know they were asking a little bit of stuff on recovery. Whether to use a deployment bag on their main or not. And
Well,
Bram,
I've been in a couple of these with Jim Jarvis, who is very much a fan of the deployment bag for parachutes of any size. I myself am not an expert on it, but after hearing him, I tend to favor them.
Right, but I think they were looking at they had 2 different ways of getting the chute out of the bag, and I guess I'm gonna say because I can't totally understand what's happening in this diagram, I tend to think that a pilot chute is the way to go, because that's the dumbest solution, and yeah.
Yeah, certainly this came about. Sorry to interrupt. Just to give a bit of background, but this came about as we were watching the New Mexico State safety review, where they had a very similar situation. They had a dual split, dual deploy parachute system with a deployment bag on the main, and from what we understand, their nose cone was connected to the bag and didn't deploy in that configuration, which caused us to worry that something similar might be, hence the pilot chute.
Sure. Yeah. Well, I mean, the pilot chute, its intention is to pull the main out of the bag. It's not to pull the bag out of the rocket.
Yes. Yeah.
Yeah.
Okay. So out of simplicity, you are suggesting the pilot chute.
Well, I can't. I mean, this is your rocket and your contest to win. And I can tell you that Spaceport is won and lost in recovery. Okay, up is easy. Anyone can put a rocket up in the sky. Getting them back down safely is where the art and science comes into this. I'm just saying I don't entirely understand your other option. This is what I'm familiar with. This is the way I have done it. And so I'm not necessarily telling you this is the way to do it, and I really can't tell you, the way you're going to do that. I mean, that's up to your team, but that's the more conventional way, I guess I would say, of doing that.
Would you like me to explain the other way, or do you?
Sure, go ahead if you want. Yeah, if you want to, maybe it'll make sense to Bram and Jimmy.
Are you able to see my mouse on the screen?
Yes, sure can.
Okay, sweet. So as the nose cone here is pulling this way, the main bag is directly connected to the eye bolt of the nose cone. And so the hope is that the suspension lines are going to be pulled out towards the avionics bay as the payload nose cone pulls the main bag upwards. So these arrows kind of indicate the direction of force.
Mm-hmm.
The hope is that the suspension lines come under tension before this kind of squiggly line does before. Because in the case that this squiggly line does come under tension before the shroud lines do, well, then the shroud lines don't get pulled at all, and nothing comes out. Yeah, that's pretty much. Can you explain it better, or?
Right, and I guess
So the inertia of the nose cone pulls off the back.
Yeah, the inertia of the nose cone pulls off the back.
So let me make sure I'm clear on this. You're counting on the inertia of the 2 separating components to pull the parachute out of the bag, right?
Yes.
Okay. on the second approach, the one towards the right on your diagram, you're using the drag of a drogue chute to pull the parachute out of the bag. Right?
Yes.
Here's something I saw was recommended to one of my teams years ago, is have it arranged so both work.
Okay, so it's a.
So that you have the option, if the inertia will pull the parachute out first, if it works. If not, you have the drogue as a backup to pull it out secondly. Now let me tell you, the team I was working with decided not to go with a backup, and they had a failed deployment on their main for that reason.
May I ask?
They decided to
meant-
go with the drogue alone and not use the inertial deployment.
Okay, thank you.
Yeah.
We will consider a way to
yeah.
do both.
Well, you used the word hope, and this is an engineering contest, and engineers don't hope. Engineers know. Okay, so what I would suggest then is if you think the inertial deploy is an option, do some ground testing, and come to the safety review with a level of confidence that says to me, yeah, we can fly that. That's going to be cool. You know, I want to see how I want to see that work. So I understand your drawing now, and I see that at least the forces add up. That should do what you're asking it to do. But come to Spaceport knowing, not hoping. Okay. And so I don't know if you'll have time to do some testing on that, but if you don't, this more traditional pilot chute, you know, that's I'm positive that'll work. So yeah.
Thank you.
Mhm.
May I ask how you would suggest doing these inertia tests on the ground? Just to give some context, we tried doing that with our recovery system last year, and on the ground, everything seemed to be working fine. We didn't account for tangling, and that's how our recovery system failed last year. How would you suggest making sure that any tests we do by pulling these apart, actually, we can definitely say with confidence it would work?
Well, all you're going to be able to test on the ground is if you're ejecting your nose cone with enough force to pull that deployment bag, right? I mean, you're not going to be able to account for the wind velocity and everything else that's going on up in the sky. But most deployment bags coordinate all your shroud lines, and that should prevent tangling.
This is for Jimmy.
yeah.
Oh, no, go ahead.
I was also going to say, when you were talking about the drogue chute, I heard, you know, tying a loop, tying a knot there, you know, for your drogue chute. Are you going to have some kind of swivel between that, between the cord and your drogue chute? Because you're going to be using that drogue chute for a very long time, because you're going to 30,000 feet. So I could see, you know, through oscillation and things, that you could twist all your shroud lines and
This
sort of.
parachute here?
Yeah, that one there. Do you have a
Yes.
swivel? Okay. All right.
Yes, we do.
Okay. Fantastic.
Yes, the question for, I believe it's Jimmy is talking about his team, like you guys opted to use just the chute to pull off your bag, and they had like a failure. What failed? Like, did it look like the parachute never caught air? Did the bag get tangled? Like, what part of the system failed? If you recall. If you can hear me. Looks like
We can
might
hear
have
you.
to-
It looks like Jimmy might be
Yeah,
frozen.
we might have to table
Yeah.
that one. Okay. We can move on then. We'll get back to you another time.
What I would suggest, I think he said New Mexico State University.
Okay. Oh.
Yeah. I would reach out to the university itself. Everybody is more than willing to share their experiences on this. Regrettably, failure is a great teacher.
Thank you.
All right, thank you very much.
Yep.
We will do our best on the ground
Okay.
here.
All right. Bram, do you have any questions, comments, concerns?
No, it seems pretty good. What's the, you said 30 feet for your shock cord for our recovery harness, sorry. What's your recovery harness made of? Is
Tubular nylon, which is 18,000 pounds tensile force. We used it last year. It worked for the drogue parachute all the way down to the ground.
Are you guys doing backup ejection charges? Or backup CO2, sorry.
Yes, we have two Raptor systems for each deployment.
Will one have a little more force in case of?
I hadn't considered that.
They both should have more force. Each one alone should have enough force to do the deployment on its own.
Yes.
Right. I think what Bram's saying that sometimes when you look at a rocket, you'll see one will have the standard cylinder and one will have, one that's it's the same diameter, but it's longer. So it has more CO2. So it's like it's sort of the Hail Mary safety feature, to produce more volume of gas to blow it out.
Yeah, they're both 35 or 42 gram cartridges, right?
Both 32 gram cartridges, and I believe if I recall correctly, we have to have at least 25. 27 or something along that. So we expect it to work, to be confirmed by ejection tests when the body tubes are here.
Okay. All right.
Okay. Any other questions from our? Yes.
I have one. Are you building your own CO2 deployment system or are you using a commercial system?
We are using two Raptor systems, the same Raptor system from Tinder Rocketry, just with different CO2 cartridge threading.
Yes.
Was that Jimmy there?
Good.
Jimmy, I still have a question. I think you might cut out when I was asking it. About your time in New Mexico, how did your deployment failure go? Did something get tangled? Did something shred? What happened to you guys that we could learn from?
Are you referring to the one that I mentioned earlier?
Yeah, where they selected to go with kind of a drogue chute instead of trying to double design or dual design it.
Well, this was actually a NASA SL launch, but it's the one that happened at Bonneville Salt Flats, and we're able to fly to 20,000 feet. So it was much more in the IREC range. Yeah. It was the University of Florida's team, and they opted to go with using only the drogue, whereas one of the reviewers recommended they add a little loop to their shock cord that ensured that when the shock cord stretched out, it would pull the bag off. They elected not to do so.
Okay.
And we were unable to see what exactly happened, but because it was like 20,000 feet, but it obviously did not deploy the parachute at that. Actually, I'm sorry, it was too far off. It was not at 20,000 feet at that point. Anyway, it did not fully deploy the main chute right away. Now it did deploy it, but it got tangled and therefore landed at too high of a velocity. They got the rocket back, but they lost points.
Yeah.
So it could have been a lot better. And I believe if they had used that dual deployment system, the backup system, they may well have had a more successful deployment.
Yeah. Okay, thank you.
Any other questions from our reviewers?
If I could prompt something, because I believe it was mentioned previously that you guys wanted to see our avionics bay that was manufactured, physically. So you can see it here. This is our avionics bay. There's a back plane that's right here. That is a printed circuit board. There are a whole bunch of board guides and it slots into the board going this way from the front, and it's retained by 2 rings that are screwed onto the front. So the slots that we are made are 3D printed plastic. We have load tested them to what the load is supposed to be for on the boards for launch, and it's meant to essentially just hold the board in there in case of vibration. We want to stick this onto a shaker table essentially to verify this, but yeah, that's essentially it's just veering from the traditional design that we used to do, which is pretty much just threaded rods with the boards on top with pins that are stacked. In this case, it's all connecting through a bus on the back with it's like a GPU, honestly. So
It's like a PC motherboard.
Yeah.
It uses a standard PCIe connection or PCI connection.
it's custom, but yeah.
Right. Yeah, I think the question Jimmy was asking, he was, that you were sharing the unfortunate situation with your body tube, and he was just, what's the status of the rest of the components? And and I think you kind of went through that. Your nose cone is largely fabricated, and your hardware, your bulkheads, your payload, all those things are ready to integrate. You just need the ready body for this thing to put it all together.
Yeah, that's pretty much where we're at the moment.
Yep. Okay. All right. So then again, like I say, let me know when you receive this stuff, and send me a photograph of your rocket all together. It doesn't have to be when it's painted and pretty and stuff like that. So just so that we know that you're coming with a rocket and not coming with parts.
Yeah.
For sure.
We'll make sure to send that.
Okay. Fantastic. Jimmy, Bram, any other questions?
Well, you make me embarrassed to have complained about Microsoft making me take 30 minutes to get into Teams when you have such a scenario trying to get your body tube. You trumped me on that one.
Yeah.
I feel for you, and I thank you for persisting against such odds, but that's what rocket people do.
We have been in the other situation before, as Brendan can attest to the fact of modifying fins in the back of a hotel parking lot before. So we know to avoid that situation.
Right. Well, one of Jim's rules, I get to make up my own rules because I'm old, is you never save anything for launch day that you can safely do ahead of time. But you know that already.
Learned it the hard way.
Yeah. Wisdom comes from experience. And experience comes from a lack of wisdom. Yeah. So, yeah. So, but yeah, anyhow.
I'm gonna use that line. Thank you.
Yeah. So anyhow, take the recording for this, email me a link, and I will send that to our friends at Ezra. If you have any questions, concerns as you go, let me know. Take some time to read up on what it takes to survive. Well, wait, I guess a whole bunch of you have already been to Spaceport, correct?
Yes, yeah, a good chunk of the team that's going to have been there.
All right. That place really sneaks up on you. You don't get sweaty. It's hot, but you're just slowly dehydrating out there. So drink lots of fluids, pay attention to each other. And I will tell you that a person who's in trouble from being in the heat, if you ask them if they're okay, they're going to say yes. Okay, that's just what they do. So ask challenging questions. What day is it? When was the last time you had something to drink? A question that they actually have to think about instead of just saying, yeah, I'm okay. Otherwise, you're going to end up in the big air-conditioned tent on an IV, and that sucks. So, all right, looking forward to seeing you there. Stay in touch so we know the status of your rocket.
Sounds good. And thank you for taking the time this evening.
Yep, absolutely. Good night.
Good night.
Thanks, Bram, Jimmy.
Thank you.
Yep.
Thanks.
Yep.
Thanks for letting me join in.
Yep.
This is fun.
Bye-bye.